Hi, I'm Alex Roman, and I'm going to be speaking today about inductive bias, what that is, and why I think it's valuable as a framework for talking about collaboration between machine learning and science. So let me introduce myself a bit. This is our team. So I'm at the University of Alabama. I'm working with Konstantin Machev and Katya Macheva. And as you can see, we have a big team, and they come from a lot of different backgrounds, from particle physics, quantum computing, machine learning, planetary science, exoplanet astrophysics. And I think of myself primarily as a machine learning researcher, although my background is in particle physics. And I've been collaborating with exoplanet astrophysicists for several years now. Broadly in our team, there are those who use the term inductive bias and those who don't natively use that term. So let me say, what is inductive bias? Pardon me. So first I have to say, what is induction? Induction in general, logical induction, is the process of going beyond observed data to make predictions about things you haven't observed yet. So a good model for this sort of toy example is just a regression problem. So in a regression problem, we're given some data, but we want to predict other points where we don't have the data. There are infinitely many models that we could possibly make, functions which are consistent with our finite set of observations. Now, most of those will make terrible predictions outside the training set. Inductive bias is what lets us select a subset and focus only on models which we find more plausible in some sense. So you might find this straight line to be a better model because it's simpler. Well, that bias towards simplicity is an inductive bias. You're using it to bias your induction towards a certain subset of all possible functions. So whenever we choose a particular method or architecture representation of our problem, we're limiting the set we can represent, and we're limiting our possible models, and that's an inductive bias. Let me talk specifically about neural nets. So a fully connected neural network, or MLP, is a way of parameterizing a function. So there's many functions that you, for a given size neural net, can't parameterize with this. It's a subset. So in all models, this is a small subset. There's a proof that, if it's infinitely wide, it's actually, universal, but that's not what I'm saying. I'm saying for a particular architecture, it's a subset. Likewise, a convolutional neural network is a neural network where you instead take a filter and you parameterize the filter, and then you convolve it with your data, and in this way it is actually a limited version of the fully connected net. It's less general. As such, it lives in a subset of that space. Now, this is appropriate in problems where you think that there is some natural dependence on some natural translation or temporal invariance. And so you think the first step should be to look at some sort of feature in the space, which is local, pardon me. So in these problems, CNNs will outperform vanilla neural networks. Let me throw out a whole bunch more examples of these things. So in machine learning, we have like regularization techniques for sparsifying or making our weights smaller or something. We have attention mechanisms. This is an inductive bias that says that we think pairwise relationships between different things are what matters. We have techniques for data augmentation to turn the model to do other things, or early stopping, which prioritizes simpler models, and so on. Generally in science, our biases look a little bit different. We might be biased towards things that respect some kind of symmetry, or maybe some equivariant property or something, causality. Or in physics-informed neural networks, we insist that the output of our neural network obey a differential equation. If you're in some particle physics setting, you might insist on conservation of mass for jets or something like that. So I'd like to talk about what this might look like in planetary science. We might, for instance, have some prior over our temperatures. It should be between 0 and 2000 K. How do we enforce that? and more examples are forthcoming. But so let me try to disentangle this picture, because I've used the word inductive bias, prior, and regularization. So are these all synonymous, or what's going on? The picture is this. Inductive biases are generally anything which limits the space of models that we're able to, that we're going to get. Explicit priors, like the temperature, is limiting our space. You are saying there's no chance that I'm going to get a model where the temperature is 3000 K or negative 100 K, which for good reason. There are also things so that is in fact limiting the space and is thus an inductive bias. There's also some kinds of regularization we do, which are secretly a prior. I wish more people knew that L2 regularization is the same as putting a Gaussian prior on your weights. There are also forms of regularization which can't neatly be expressed as priors, such as dropout or early stopping, but are in fact inductive biases. Okay, so broadly though, I think that in this collaboration, we have machine learning, which teaches us how to build models and fit models to the data, and we have domain experts who understand the problem and know what must be true for their model. And I think good collaboration looks like taking what must be true and somehow baking it into the model, and so that can simplify our lives and require less data and less compute. So let me give you a couple examples of something where I've kind of done this. So back in 2022, I participated in the Aerial Data Challenge, which, if you're not familiar, I think the next talk is going to address this. So in that year, the task was to predict the posterior for a particular exoplanet transit spectrum without doing the Bayesian retrieval. So you train a neural network, for instance, and try to predict directly what it should be. So this depends on the modulation, but really the modulation is telling you, what fraction of the star's light is blocked out. So geometrically, this is like this formula. I don't have time to go into it too much, but basically what we did was, so we think that what really matters is sort of the thickness of that little annulus of light that's coming to us from the star, that's going through the planet, that's being absorbed and having its fingerprint imprinted. And okay, that's not so surprising, but we pre-process the data to extract the height of that thing. And we have reason to believe that the standard deviation of that with respect to the spectral bins is proportional to the scale height, which in turn is proportional to the temperature. And so all of this is quite straightforward to do analytically as a pre-processing step, and it turns out is very helpful to the model. Further, the standardized spectrum is entirely composition dependent, and we have a paper actually exploring all these ideas. So if you're interested in knowing why I say these things or what this precisely means, please check out our paper. I also don't have time to talk about it too much, but in this competition we use this ansatz, which is sort of another way of encoding what we think the answer should be, to make our model's life easier. By the way, we actually got first place in the regular track of that year's competition. Let me close with one more case study. So this is some other work that we've done with degeneracies. So let me step back to this elegant piece of math called the Buckingham pi theorem. What it says is that any physical model can be written in terms of these dimensionless combinations of the inputs to that system. So in the case of a transit spectrum, we know it depends on these 7 things, say. But basically, these 7 constants physically have dimensions of length, mass, and time. And so that's three physical dimensions, and we have 7 parameters. So it turns out there's only 4 distinct combinations that we can make dimensionless. And these are called the Buckingham pi groups. And they're drawn here in this over here. And it's a very surprising result from this pi theorem that any model can be represented as some function of these four things, basically. For more details, please see our paper. And since we seem to have 7 degrees of freedom, but we know in reality there's 4, there's actually different spectra, or pardon me, different atmospheres, which will result in indistinguishable spectra. And so that means these degeneracies exist. I'll give you one example. For instance, if you were able to somehow double the mass, mean molecular mass of the atmosphere, that would weigh it down. But if you simultaneously doubled the temperature, it would puff it back up again. And ceteris paribus, you would have exactly the same observation. So I'll give a caveat that this is true. In our paper, we're analyzing a simplified model, but we have ongoing work to try to show that this is true for more complicated sophisticated forward models like Tau-Rex and Poseidon. So keep a lookout for this paper. I think it's a very interesting topic. And if true, this means that we can sort of parameterize our problem and make it explicitly respect dimensions. So we have to get our units correct. Okay, I'll just close here and thank everyone for listening. I won't recapitulate, but because I'm running out of time. So thank you very much.